hope all of you can hear me, right?
Yes, sir.
Okay. So Nabil and Hanifa, can you tell me what is the intermediate form, Samaya, in this reaction? Is the intermediate going to be this one? Or is it going to be this one? Or is it
H and BR?
Yeah, no, in the third question, in this one, what is the intermediate? Yeah,
Sir, fourth option.
yeah.
Fourth option.
What, Nabil, fourth option?
Yeah.
And Samaira, Hanifa?
So first one.
Yeah, first one only. This first one. Reason being, among all HX, only HBr shows peroxide effect, right? HCl does not show peroxide effect. Even if you have taken peroxide, it is going to add in a way in which it used to add without peroxide. Is it clear? So how HCl used to add on double bond? HCl first dissociate into H plus and Cl minus. H plus goes and add itself to double bond in a Markovnikov way. Okay. So a more stable carbocation is found. That was the Markovnikov addition. And we are going to do the same thing. This is the addition of H plus. Okay, and which has led to the formation of a tertiary cation. You can see this is tertiary, which it has formed on this position. Okay, because this is tertiary cation. And now you are going to put Cl minus here. So mode of addition of HCl or the mechanism of HCl remains same. It doesn't change in the presence of peroxide. That you should remember. But only HBr mechanism changes. Normally it is H plus minus H plus attacks and Br minus attacks in the second step. Okay, after more stable carbocation is formed, right? On the other hand, HBr in the presence of peroxide breaks. Okay, peroxide actually forms a break H radical and forms a Br radical. Br radical will attack on double bond such that a more stable radical is formed. So first Br radical attack. Okay. So if suppose you think that this is a very, very important question. Okay. So be careful with this, and most of the people may go wrong, not because they don't know. It is because in a hurry, in examination pressure, they can tick mark the wrong option. Is it clear? So suppose someone may think that peroxide is here, peroxide is going to break H radical and will release Cl radical, and Cl radical will go and attach itself to the double bond, leading to the formation of a more stable more stable radical. Okay, if suppose the mechanism is free radical, then we would have expected this third option. But we should know that HCl do not show peroxide effect. So the mechanism will remain same as it used to be without peroxide. Okay, so this is going to be the answer. So I hope this is clear to all of you. This is the question which has been asked in JEE Main, JEE Advanced. Okay, NEET, everywhere, NEET 2-3 times in 2-3 ways it has been asked. Is it clear?
Yes, sir.
Okay, so now the question also is being asked on the reason. What is the reason? Yeah, tell me. What is the reason? So this is the mechanism. Normally without peroxide, HBr breaks as H plus and Br minus. In the presence of peroxide, the peroxide actually breaks very easily, okay, because of the OO bond, okay, and it breaks away the H radical. O radical is there, it abstract H radical, and Br radical is generated, right? And this Br radical adds itself to the double bond. Okay, it will add itself to the terminal double bonds as that are more stable. Secondary radical is formed, 2-degree radical is more stable. Okay, and then this radical is will again abstract H radical from HBr. And a Br radical, a new Br radical is regenerated with some other HBr molecule. This Br radical will go and attack again on the double bond, some fresh alkene, and that's how the reaction keeps on progressing. So these two steps are chain propagation step. Okay, they are like cyclic mechanism, okay, which is happening in a cyclic way. Okay, and this is the initiation mechanism in which the peroxide abstract H from HBr, H radical and Br radical is obtained first time. Okay, so why HCl and HF don't give peroxide addition? The reason is this step. You can write for HF and HCl, the bond is stronger. Okay, because halogens are smaller, their bonds are smaller, and they are stronger. So they can't be abstracted easily by the peroxide. So F radical or Cl radical don't form. There is another way of saying this same statement is F radical and Cl radical are unstable. That's why they don't form. And it is difficult to break the H from HF and H radical from HF and HCl. And there is one more way of saying, because why I am telling all these ways, because they all of these ways have been asked in JEE Advanced as statement, and they have been asked in NEET as reason assertion question. Okay, so you need to have the full confidence, full knowledge of whatever you are, whatever is being done. Okay, because in reason assertion, though they don't ask any numerical or they don't say anything, they don't give you anything to solve, but still they can check the knowledge in a more in-depth way, because the statement which are written need to be analyzed very thoroughly. Okay, so for HF and HCl, this step is not going to happen. Okay, their bonds are stronger. F radical and Cl radical are formed are unstable, but Br radical can form easily. Its bond can break easily. Or you can say this step heat of reaction is positive. Positive heat of reaction means what? Positive heat of reaction means heat need to be supplied. It is endothermic step. In the case of HF and HCl. So that's why HF and HCl don't give F radical and Cl radical. Okay, in the presence of peroxide. Because how long can you give that heat? It is not possible. But in HI, the bond is very weak and it can be abstracted very easily by peroxide. So in HI, the problem is something different. In HI, the problem is not the stronger bond between H and X, right? But the problem is something else. In HI, the H radical is abstracted very easily because HI bond is weak. I radical is generated. It is very stable. But my dear students, you know that I belongs to fifth period, right? And being in the fifth, because it is a fifth period, remember that unpaired electron radical, which we are calling it as a radical, that will be present in the 5p orbital of iodine, which is a very, very large, very, very dispersed over a large area. So I radical breaks away from H very easily by peroxide, but I radical is very stable. Just formation of I radical will not take the reaction ahead. That I radical need to add itself to the double bond as this Br radical is doing, as you can see over here. But that doesn't happen because I radical is too weak, too stable, being very large, the electron density is dispersed over a large area. It doesn't add itself to the double bond, or it is unable to break the pi bond also. Okay, and that is the reason why HI don't exhibit peroxide effect. So for HF, HCl and HI, you are going to add them in a normal way as you were doing without peroxide. Okay, they don't there, that is electrophilic addition, Markovnikov addition. So I hope this is clear to all of you. Hanifa, Nabil, Samaira, any doubts in this? You can tell me quickly. Okay, this question you can do, very easy question. This is the peroxide. It is also written in this way. This is the most famous peroxide which is given to you. So don't get confused. Sometimes what we may get confused by looking at the molecule, we see, oh, such a large molecule we have not seen, and what is going to happen when we don't know its formula. So don't worry about that. Okay, this is just a peroxide, benzoyl peroxide. Yeah, this is HBr, so it is going to be the Markovnikov anti-Markovnikov addition of HBr. Yeah, Nabil, what is going to happen? Hanifa, Samaira.
The first one.
Yeah, first one. Right. Correct. So first one is going to be the answer. Now let's move ahead, and now we need to discuss the halogenation of aromatic compounds. Okay. In aromatic compound, though there are many type of aromatic compound, they have 4n+2 electrons moving in a cyclic resonance. That's why they are very stable. But there are many aromatic compounds. Okay, you might have studied in your class 11th, like benzene, naphthalene. These are the most common. But in this chapter, we are mostly dealing with benzene. Okay, but that doesn't mean the benzene is the only aromatic compound. Furan is the aromatic compound which has oxygen. Cyclopentadienyl anion is aromatic. Cyclopropynyl cation is aromatic. Okay, there are a lot of aromatic compounds, right? Other aromatic compounds. Okay, so how you are going to attach uh, chlorine to benzene? That's the question. Okay, so how you are going to attach? Just I would like to recall that how we attach chlorine to methane. What method we adopted? We used photohalogenation. Okay, we use Cl2 and we use light. Light provided energy to break the Cl2 into Cl radical. Cl radical abstracted the H radical. Carbon radical found carbon radical again attacked on Cl2 to form CH3Cl, and that was free radical halogenation for, or it was a substitution reaction in which the H was displaced by Cl, but the intermediates involved were radicals, so that was free radical. In bending, if you want to, the thing is you should use benzene, and if you take Cl2 and if you take sunlight, what happens? What you get? Yeah, tell me, Nabil, Hanifa, Samaira, quickly tell me what you will get. You will not see H displaced by Cl. What you will observe is addition of chlorine, and you will get benzene hexachloride. Okay, this is also commercially known as lignin, and it is an insecticide. Okay, so this is addition reaction. Suppose if someone tell you that you need to put 1 Cl, how you are going to do that? First of all, you can't put 1 Cl, only 1 Cl. Actually, if you want to attach 1 Cl to the benzene, you need to remove H from that position, because in order to keep the number of carbon atoms same. Okay, because you can't exceed the number of carbon I can't exceed the number of bonds, not the carbon atom. No, you can't exceed the number of bonds, you can't exceed the tetravalency. Okay, because carbon can make 4 bonds. So suppose if you are putting Cl, you need to remove H from that position. So it is a substitution reaction. Okay, it is an aromatic substitution reaction, and because it is taking place on a benzene substrate, and it is electrophilic aromatic substitution reaction. Okay, what do you mean by electrophile? Why it can't be nucleophile? The reason is uh, benzene ring has 6p electrons, as you know, and these p orbitals actually are in resonance. Okay, you might have seen, and that is the reason why benzene is aromatic. Okay, the 6 electrons are actually delocalized. Okay, and there is an electron cloud above and below the benzene. So suppose if you want Cl to come and get attached to the benzene, that Cl should not be Cl minus, because that will be repelled away. That Cl should not be Cl radical. Okay, because with radical addition will happen. Okay, that Cl should be Cl plus, if you want to do this kind of thing. Okay, so in general, I have shown over here is E plus, right? Electrophile. E plus is going to come and take away the electron density away from the benzene, but means you can expect something reaction to happen if this is a plus, and that's why this is known as electrophilic addition reaction. Okay, so how you will generate this E plus? It is, suppose Cl plus you need to take, then only it can react with benzene. Okay, or and you need to create Cl plus from chlorine, which is the most common source of Cl. So you need to take some Lewis acid catalyst. Okay, this is Lewis acid. What are Lewis acids? Who can tell me? Samaira, Nabil. AlCl3 also you can use. This should be anhydrous. Hanifa means without water. So you can generate Cl plus, you can generate Br plus from by taking chlorine and Lewis acid. Okay. So what this Lewis acid do? Lewis acid is a molecule which can accept electron pair from any other molecule.
Empty orbitals.
Yeah, it has empty orbital. Very good. Yeah. So I will put a box. That's the key thing. Very good. Okay. So FeCl3, AlCl3, or you can take Cl2Fe also. So don't get confused. Sometimes it is written as Cl2Fe, because the Fe will react with Cl2 and it will form FeCl3. Okay. So FeCl3 or AlCl3 have empty orbital, and they will and you take Cl2 and the Cl has lone pairs. So this FeCl3, Fe gets the lone pair from chlorine atom, okay, and it forms a bond. And when you see this bond forming, right? So you see over here is that earlier it was Cl-Cl bond, but now it is Cl and Cl plus. Okay, it has become more polar. Earlier it was non-polar, so now it has become more polar once the chlorine atom get attached to Lewis acid. Okay, and it is susceptible to cleavage. And how it will cleave? It will cleave heterolytically. Okay, because this chlorine has plus charge, so while breaking it will take both the electron pair with itself, so it will come out as Cl minus, and this chlorine which is highlighted will be left behind as Cl plus, which is an electrophile or an electron loving species or an electron deficient species. Okay, so that's how you generate Cl plus. Is it clear to all of you? Okay, normally Cl plus is not, it is an intermediate, it is very unstable, you can't get it on its own. You need to take chlorine and you need to take Lewis acid catalyst, then only Cl plus will be generated. Okay, the next thing is what this Cl plus will do. You have taken benzene ring. So this benzene ring has a pi electron density above and below the ring. So this Cl plus will go and abstract the pi electron of this benzene. Okay, and this type of intermediate is going to form. The pi electrons which were the part of the benzene ring, now they are pulled out by Cl. Okay, and that's how we have a plus charge. Okay, what do you call this intermediate? What is the name of this intermediate? Yeah, can any one of you tell me what this intermediate is known as? Yeah, Samara, Darshan, Nabil, Anifa. This intermediate, when an electrophile come and take away the electron density of the benzene, this is known as sigma complex. Okay, this is also known as Wheelan intermediate. Okay, the Cl plus will come and take the pi electron outside, that it will have plus charge. Okay, this carbon will not have plus charge. Okay, this will have, because the pi still this, the carbon on which Cl is attached has 4 bonds, so that is neutral. Okay, so Cl plus and the plus will come on the ring. This plus will not going to stay at one place, because this plus it is a part of a ring, and which has 2 more pi bond left still inside the ring. It can take the electron density from the adjacent pi bond. This adjacent pi bond will rotate like this. Okay, the plus charge will come on this carbon, and it can also come on this carbon. So this is resonance stabilized. Sigma complex is stabilized by resonance, right? And but it doesn't mean that it is very stable. It is a difficult step, and that's why this is the rate determining step, RDS. It is the slow step. Attack of electrophile on the benzene ring leading to the formation of a sigma complex is the difficult step, because benzene earlier was neutral, it was very stable because of its resonance, and now electrophile has come and it has snatched one of the pi electron of the benzene. It has taken out, though the intermediate which is formed is still stabilized by resonance, as you can see, but it has a charge, and now it is not aromatic, because now it is not having 6 electrons moving inside the ring. It is just having 4 electrons, right? Okay, so this is sigma complex. Formation of sigma complex is RDS, slowest step. This sigma complex is not the end of the reaction, because as we discussed, this is still an intermediate. Okay, this is not stable. We need to get back our benzene ring, that is the stable and that is the final product. Okay, so how that benzene is going to come back? We need to create the benzene again. Okay, so remember this Cl minus was taken away by FeCl3. Okay, that Cl minus can be released back and it can take away the H plus. H plus means the H without the electron pair. So both the electron pair will be left behind on the benzene ring itself and they will get into the benzene. And that's how the sigma complex will get back the pair of electron which it has lost to Cl plus earlier in the step 1. Now the loss of H plus from the position where the Cl plus has attached as well, okay, will neutralize the sigma complex and we have benzene ring again. Okay, but in this whole process, what has happened? The Cl plus which attacked the ring at a position and that was displaced H plus. Okay, so this is a substitution reaction, but the species which involved in this are electrophiles Cl plus and H plus. One electrophile came and joined itself to the benzene ring. Another electrophile was removed. H plus was removed. So it is an electrophilic substitution reaction. And because it is happening on the aromatic compound, this is known as EAS reaction. Okay, so these are the products. And that's how we connect chlorine to benzene. Right? This is the way in which we connect the chlorine to benzene. Okay. So this is known as EAS reaction. Okay. Now the question is, you will not get always benzene. You may get substituted benzenes also. Suppose if I ask you, if I give you benzene and if I ask you to do its chlorination, and if I ask you how many different chlorobenzenes will form, you will say only one. Okay, one. Why one? Because benzene without any substituent, all 6 carbon are same. Okay, you can put Cl anywhere. Okay, at this point, it's a regular hexagon. It doesn't matter. Okay, so you will get only one type of chlorobenzene. Okay, and this can be done by taking Cl2 and FeCl3 and the mechanism we discussed just now. And this is EAS reaction. Let me tell you one more thing. Okay, CH3 Cl2, okay, and H nu. But if you take Cl2 and light, and if there is a carbon outside the benzene connected to just directly connected to benzene, this is toluene, right? The common name of this methyl benzene is toluene. So now Cl radicals will be generated and they will break the H. And H will be broken very easily from the CH3 group because it will be resonance stabilized. Is it clear? In this way, okay. This H can be abstracted. This is benzylic hydrogen. And this will attack on Cl2, another Cl2 molecule, and that's how we are going to get benzyl chloride. Okay, so this is a different type of chlorination. This is not EAS reaction. This is photohalogenation of alkyl group. This is the alkyl group. Okay, and this reaction is different. This is the chlorination of aryl group. Okay, aromatic ring benzene. Okay, which was EAS reaction. The lower one was photohalogenation reaction. Okay, is it clear? But if someone ask you to do electrophilic aromatic substitution, means you need to attach the Br or Cl on the benzene ring if there is already one group. So what I am going to get here, can any one of you tell me what will be the product of this reaction? Yeah, Darshan, Hanifa, Samaira, Nabil, tell me quickly. This is toluene, common name methylbenzene. So where the, suppose if someone give you Br2 and light, then you will attach the Br on CS3. That's a photohalogenation reaction. But if someone asks you to do the electrophilic aromatic substitution, then you are going to attach the bromine to the benzene ring. But where on benzene ring? Okay, is it like chlorobenzene? No. Chlorobenzene, all 6 carbon were same, it was symmetrical. But in this case, it's not same. Okay, you can attach the Br at these positions. These positions are known as ortho positions. The position adjacent to the group which is present. Okay, or you can put the Br at the meta positions. These are the meta positions. Or you can put the Br at this position which is directly opposite to the methyl. This is para position. It is represented by P. So Br plus will be created, and where should I put this Br plus? Tell me. Samara, any idea? Hanifa, Darshan and Nabil. Where should I put Br plus with respect to methyl? Should I attach it at ortho position, meta position, or para position? Or anywhere, it doesn't matter? What should be the answer? Samara, any idea? Okay, so let me tell you, either you will get a mixture of ortho and para substituted compounds, or you will get a meta substituted compound. Clear? That's the thing. Electron donating groups will give you ortho para products in electrophilic aromatic substitution reaction. Electron withdrawing groups will give meta substituted products. Okay, they are going to give meta substituted products in electrophilic aromatic substitution reaction. Okay, so first of all, let me show you the answer to these three. So this is electron donating, and how will you know it is an electron donating group? One is, it just like an alkyl group, it is an electron donating. Br is also electron donating because it has lone pair, and those lone pair will get into the benzene ring by the mean of resonance. NO2 is electron withdrawing. So this is meta directing. Meta directing or ortho para directing is a way to know or predict what kind of product will form this upon doing ES of a substituted benzene. The substituent which is already present on the benzene like CH3, Br or NO2 will direct the new group or electrophile which is getting joined to the benzene. If the group which is already present directs the incoming electrophile, the second electrophile, at ortho towards ortho or para position, then that group is known as OP directing. And under this condition, ortho and para products are formed as major. If the group has lone pair, that is also electron donating group. Okay, and that is also ortho para directing. But if you have strongly electron withdrawing group, and how will you know the one? I will show you. Then it is meta directing. So it will direct the incoming electrophile to meta position. So this is the meta position. So you are going to get meta bromo nitrobenzene. That will be the answer. So let me show you the answers. Ortho and para will be formed simultaneously. You can't have only ortho or can't have only para, or both will form. But you or meta will form. They are mutually exclusive. You can't have ortho para together and meta together. Right? Clear? So why it is
Yes,
happening? Yeah, you can see the answers. Okay, why it is happening, I will explain you. The reason is this. Okay. You need to understand, Samira, how the CS3 is giving electron pair. Okay, and this effect, what this effect is known as? Can any one of you tell me? This CS3 is plus I effect. Okay, it exerts plus I effect because it is not electronegative enough. So it exhibits plus I effect, inductive effect. Okay, this is one thing. But effect which is more effective than plus I effect. Plus I effect is just the sigma electron. They don't go here and there. They just remain in their bond. They get shifted toward the benzene. Because when CS3 is not very electronegative, so that's why the electron will not be pulled by CS3. Okay, and they will be just remain in their bond, and they will be towards benzene. That is plus I effect, which is a very weak effect. But a more prominent effect is hyperconjugation effect. This is positive hyperconjugation effect. This is also known by the symbol of plus. In this hyperconjugation, what happens? The electron density of the CH bond gets into the benzene ring. It get mixed up with the pi electron. Okay, this electron density is so. In order to show that mixing up, I am drawing structure one by one structures, right? So you can see over here, this electron density will get shifted towards the benzene, and the carbon of the benzene, the pi electron gets shifted, has to move aside, has to be moved aside, because otherwise this carbon will make more than 4 bond. If the electron are coming from the top and the double bond is forming, this pi bond will shift sideways and the minus will come here. So that's the way to show that the electron density of the CH bond is getting. Now you can see that no bond is shown over here between carbon and hydrogen, which means that this electron density has got into the benzene ring, and at first it has appeared on the ortho position. But this is not going to, so ortho position is enriched by hyperconjugation effect, which brings in the electron of CH bond into the benzene ring. Now this negative charge is not going to stay at ortho, it is going to move ahead in the benzene ring. So it is going to, because there are more double bond. in the ring. So this minus will push the double bond which is ahead of this. Okay, the minus will appear at the para position, the same electron density. And again, it can move ahead and it can push the pi bond which is ahead of it. So this electron density can get accumulated at another ortho position. And now this electron density can get back to the CH bond. Okay, this is a way of actual structure is the mixed form. And what I'm trying to say, I'm trying to say that some of the electron density of the CH bond has got into the benzene ring and it has enriched the benzene. But actually, it doesn't mean that all the position of the benzene ring are enriched by equal amount. You can clearly see that or the electron density due to hyperconjugation will enrich the ortho and para positions more. Okay, because you need to draw this arrow, you need to move electrons and you need to see where the electrons are coming one by one positions, where the which positions are enriched more, okay, in terms of electron density. Okay, these are ortho para positions. And remember, we were doing electrophilic aromatic substitution. Br2 FeBr3 generated Br plus. Why? Because Br minus was taken away by FeBr3, right? So that Br plus, now you can clearly think where it will attach itself. Okay. Are all positions can the Br plus attach itself on the toluene ring at all position with the equal ease, or there are some positions where the Br plus can attach itself more easily? Which positions are these? These are the positions where the electron density is more. So ortho and para positions. Okay. That's why it is ortho para directing. Is it clear?
Yes, sir.
So this is very important. Just remember it. And this hyperconjugation effect I have seen from last so many years, that this is the effect which most of the my students forget. Okay, because this is not, this is difficult to imagine. Even the people uh, discovered it later. Okay, they were not expecting the sigma electron density to get into mixed the benzene. So that's why it is very important. Another one is bromobenzene, but bromobenzene is also enriching the ortho and para positions because there is a lone pair. So if you have a group having lone pair, that will be ortho para directing. Just keep this in mind, because those lone pair electron density will get mixed up with the electron density of the benzene ring, and you can draw one by one structure. The lone pair form double bond with benzene, and the double bond of the benzene will shift to the ortho position, right? In this one. So this again has created the same scenario, and so you can write the average hybrid structure and where the Cl plus will attach itself. Cl plus will attach itself with more ease at the positions which are more rich in electron density, and these are orthopara positions. So you can see over here. So this again is orthopara directing. Okay. Now what happened to nitro N? So let me tell you the thumb rule. Strongly electron withdrawing groups like NO2, okay, strongly electron withdrawing group, how will you know? There is one common feature, either they will have plus charge or they will have a group of electronegative atom like in CF3 or CCl3, or they have plus charge on them, directly on them. or they will have pi electron, and those pi electrons have some electronegative atom like SO3Hc and COH. Okay, and those pi electrons you will not expect such groups to give electron density to benzene, like the way in which we did these in the above cases. Okay, the electron density was getting into the benzene, but in these cases the electron density will be taken away from the benzene. So you can see this is the structure of nitrobenzene, and I have put this NO2 group into more detailed. This is the detailed structure, as you can see over here. This can pull the N is plus, there is no lone pair. Okay, there is no lone pair. So there is no lone pair, it will, and it has a plus charge, and it is also connected to oxygen, which is another electronegative atom. So this plus will pull the electron density towards itself. So I have moved this electron density out, and this is known as minus R effect or minus M effect. Okay, minus R or minus M means the electron density is being pulled out by resonance. Okay, with charge, this pi electron which is there inside, it will go like this. Okay, you can see, and this carbon atom is devoid of the electron density, so it will have positive charge on it. So this positive charge is not going to stay here, it is going to pull the electron density from a pi bond which is ahead of it in the ring. So this positive charge has pulled the electron density, and I have put an arrow to show you how it is happening. Okay, another one is this. Okay, and it will come on this. Okay, right, and it will get back to its original position. Okay, so these are the structures, one by one, resonance structures of nitrobenzene. Actually, this is one by one. Okay, but actual structure will be, because electron don't move, they come this at this place, at that place, and that place one by one. It will be simultaneously happening. Okay, so actual structure will be the average structure of all these structure, which is known as resonance hybrid. Okay, so you can see that delta plus will be generated at ortho and para position due to minus R effect. It is the effect which pulls the electron density out of the benzene ring by the phenomena of resonance. Okay, now if the electrophile comes and attack on the benzene, where do you expect that E plus which want electron to get attached to the benzene? Yeah, tell me. Where do you expect it to get attached more easily? At the ortho or para positions where already there is a positive charge, or at the meta position?
At the
Meta
meta.
position.
Yeah, meta position, because at ortho and para position it will be repelled away. Positive will be repelling the positive. Okay. So meta position. Yeah. So this is Samara, Hanifa, Darshan. This is meta directing. Okay. This is the major product. And there is one more thing which I can ask you people is, will it be an activating group or deactivating group? If I ask activating or deactivating, activating Nabil or deactivating?
Yes.
Which one?
Activating group.
No, this is deactivating, strongly deactivating. Okay, and what does this mean? If I'm asking you activating or deactivating, I'm trying to ask you to compare the rate of nitrobenzene with benzene. So is the electrophilic aromatic substitution going to occur more easily on the nitrobenzene or less easily as on the nitrobenzene as compared to benzene? So it is going to occur with more difficulty. The rate is going to be less because
Yes, slower.
yeah, slower. Very good. So because it is the attack of electrophile, and what electrophile wants? Electrophile want more electrons, but the electron density is pulled out. It is pulled outside by the NO2 group. So the ring has overall become electron deficient. Okay. So though the deficiency is more on ortho and para positions, but and meta position is somewhat saved from that positive charge, but it is still overall the electron density has been moved out. Okay. And because of this, the overall rate of reaction will be slower. Okay. And let me tell you the actual fact. This nitrobenzene will react million times, okay, slowly than benzene towards electrophilic aromatic substitution. Okay. So it is very slow reaction. Okay. But if you have electron donating groups like methyl or groups which can give electron by resonance, for example NH2, which has a lone pair, OH, which has a lone pair, O minus, which has 3 lone pair. Okay. Such groups are strongly activated, very highly activated. They are so activating that even you will not require Lewis acid, okay, to do their halogenation, right? So this is the whole thing which I explained. So let's do some question, and those questions will help us to understand these things more easily. So this is the first question from NEET, but it is a very good question and good for JEE. Very nice question. Yeah. So this is first of all C7H8. Okay. And now my question is what this molecule is. It can have billions and millions of possibilities. And the structure is not given, only the formula is given. So my dear students, you don't have to worry. You need to look at the option. So all the options have toluene, the word toluene in them. And toluene means this group. Yeah, and this also satisfies the formula which is given in the question. Okay, there are 7 carbon and there are 8 hydrogen. Okay, and this is C7H8. Now this is Cl2 heat or light. So without the Lewis acid catalyst. So this is halogenation. Is it the halogenation of the alkyl side chain, or is it the halogenation of the aromatic ring? That you need to tell and think. Yeah, tell me. And think how the halogenation of benzene occurred. The halogenation of benzene occurred with the Lewis acid, and no Lewis acid is there. If you take heat or light, Cl radicals will form, and those radical, if no alkyl group is there, they will attach on benzene. But if alkyl group is there, the more easy way is to get attached to that alkyl group by doing free radical substitution reaction, and that is photohalogenation. Okay, right? So this is what is going to happen with 1 mole of Cl2. But you don't have only 1 mole, you have 3 mole. So it is going to happen again and again. I mean to say 2 more time. Okay. And if it is going to happen 2 more time, what is going to be the structure of A? Tell me. Samaira, Nabil. Yeah, tell me quickly. Yeah. What's going to be the structure of A? This is just like the doing the chlorination 3 times. So CCl3 will come. Okay. Now this is bromination in the presence of Fe. Fe and Br2 will form react and they will form Br2. Fe and Br2 is Br2 and FeBr. Okay, Lewis acid catalyst will come. Br plus will form. Okay. This is the electrophilic aromatic substitution reaction of benzene ring. But where the Br plus is going to attach itself on CCl3PH. You need to know its orientation and reactivity. Is it orthopara directing or is it meta directing? Yeah, Nabi. Samaira, Hanifa, Darshan, tell me. You need
Meta directing.
which directing? Yeah,
Meta.
meta directing. Exactly. Very good. So why you said meta?
Because that is an electron withdrawing group.
Yeah,
CCl3.
yeah, very good. That is the electron withdrawing group. That is the reason. And let me tell you more detail about it. That is strongly electron withdrawing group. Yeah. And let me tell you one more detail, minute detail, which very less number of students actually get into this detail and they don't remember it. They forget even toluene also, which is the most common. So toluene actually, this is the positive hyperconjugation. Plus it, the electron density of the sigma CH bond was getting into the benzene because CH bond was not very electronegative. So it is not having problem to overlap with the pi bond and give its electron density. But in CCl3, it is happening in opposite manner. Okay, there are sigma bond, but you can't afford this CCl sigma bond can't afford to give its electron density to benzene because Cl is very electronegative. Okay, so the something reversed happen in this way. Okay, so this is also the electron density of the ring getting mixed up with sigma bond. So it is hyperconjugation, but it is negative hyperconjugation effect, which will create a positive charge at ortho and para position. Clear? So this is meta directing. So what we will do, we will put CCl3 and Br at the meta position. Now zinc HCl. Zinc HCl is a very good reducing agent. Actually, zinc has a tendency to give electrons, and HCl will give H plus. And that's how, and it is a good way to reduce alkyl halides. Okay, the CCl3, you can think CCl3 as CCl2 and Cl minus and CCl2 plus. This is the benzene, and the zinc will give 2 electrons. If it gives 2 electrons, this CCl2 will become minus. Okay, after getting electron from the zinc, it was plus because of the departure of Cl minus. And now H plus will come and it will make it CH. Again, one more Cl minus will break away. You will have plus charge. 2 more electron come from zinc. It will become minus charge. H plus will come and join to carbon. It will become CH. Okay, and again you will have CH. Okay, so this is actually meta-bromotoluene. So A is the right answer. The CCl3 will become CH3. But why we are not reducing bromine? That is also a halogen. That can be the question which can come to your mind. Okay, the reason is this bromine is in resonance with the benzene. And this carbon bromine bond, due to its resonance, as you can see over here, wherever this resonance is, the outer group is interacting with the benzene by the means of resonance. That group, the bond between the group and the benzene acquired double bond character. You can see at all these places. So this bromine group is having a double bond character. So it is not easy to reduce this bromine. That's why we have kept it untouched. But it was very easy to reduce CCl3 to CH3 because those three Cl were not directly connected to benzene. Okay, so the answer is going to be CH3 with a bromine group at the meta position. So meta-bromotoluene. This is going to be the final answer. Okay, very good question. In fact, it is difficult and many of the students can do it wrong. Okay, so be careful, right? Very good question. Okay, though very simple. And this is the question which is given in JEE advanced. Okay, but very simple. It is useful for all of you. Okay, now you can tell me where should I, so this is electrophilic aromatic substitution reaction. It is Br to Fe. Now you can tell me where should I, and this is going to put Br plus. Okay, and Fe Br4 minus. This Br plus is going to go and attach itself to the benzene ring. But where? That's the question. So what is going to be the answer? Nabil, Hanifa, Samaira. Very basic question, but very important. Yeah. So there are two rings. So first of all, you need to decide which ring is more electron rich. So I told you the trick. You need to look, you don't have to look at the entire molecule. You just have to look at the group which is directly connected to the benzene and how that group is interacting with the benzene. On that basis, you need to decide whether the benzene is having more electron density or less electron density. An electrophile is going to attach itself out of the two rings. If one is electron rich and another is electron deficient, the electrophile is going to choose the ring which is more rich in electron density because electrophile is an electron loving species. Okay. So tell me what is going to be the answer. Very simple question, but very important. And hint already I gave that you will attach Br to benzene. Either of the two, either the right benzene ring or the left one. Because Br to Fe is given. So answer is going to be out of option A, B and D. Any one of these, because in these three options only we are having that Br connected to benzene. Okay, clear? Tell me, Samira, Hanifa, just right, Nabil. Any idea? Yeah. The answer, actually, a lot of questions came in past examination, okay, of this kind. Very simple. This is D is going to be the answer. Let me tell you a very simple way. This is nitrogen, and nitrogen has a lone pair. Okay, not all the nitrogen are having a lone pair. No, NO2 is not having a lone pair. NO2 was having plus charge. NH3 plus is also not having a lone pair because that is having a plus charge. If it is neutral, it is having a lone pair. Okay, and if there is a lone pair, that lone pair will interact with the pi electron density of the benzene ring because it is adjacent, it is directly connected to the benzene ring, and it is going to give its electron density. This is plus R exerting group. And that's the way the electron density of the benzene ring is going to get enriched at the ortho and para position. This is just like aniline, but not like NO2, not like NH3 plus. They were strongly electron withdrawing and meta directing. This is like NH2. Okay, and this group has a pi bond. And at the other end of the pi bond, there is one more electronegative atom sitting, as you can see over here. So what it is going to do, it is going to pull the electron density of the benzene ring towards itself. Okay, and the benzene ring, what will happen? It will have a positive charge immediately at ortho position. Then it will, that positive charge is going to move at ortho, para, and ortho positions. Okay. So this is the whole picture that should come to your mind by considering the resonance effect of the groups which are directly connected to the benzene ring. Okay, now you can decide which ring is more rich and which ring is deficient. The ring on the right hand side is more rich in electron density. At ortho para positions are more rich. Okay, and the Br can attach itself more easily to these positions. This as compared to the left ring, which has positive charge and overall the electron density is sucked out of the benzene ring, so that is less electron rich and less reactive, deactivated ring. The right one is activated, and now the question is, where should I put the Br? And the answer is very obvious. Br will attach itself at ortho and para positions. Okay, so this is going to be the answer. In this case, the ortho will be formed in less amount because this group as a whole is very big. So because of this bigger group, the ortho positions will be more repelled and the electrophile will not get attached to ortho positions in more amount. So para product will be the major product in this. So I hope this is clear. Very simple question. Very, very important. Okay. Now let's move to some other ways of putting halogens. These were the direct ways. And the direct ways of putting halogen. And we have also not only seen how to put halogen, we have also seen the electron, how the group which is attached to benzene affect its electron density and make it more reactive or less reactive as compared to benzene, and how that group affect the orientation of the electrophile which is being joined to that group. Okay. Now indirect way of, so those were direct ways. You can take Cl2 and FeCl3 or AlCl3 to put Cl plus on that benzene. You can be at Br2Fe. Okay. But let me tell you, fluorination and iodination can't be carried out directly in a way in which we did fluorination and bromination of benzene. For fluorination, the reason and the problems are quite obvious. Fluorination is highly exothermic and uncontrollable reaction. You can't control it. Okay, if you can't control it, means it will be too exothermic and the bonds will break, and or you will have fluorine at all the positions. Okay, you can't control what is the product which is forming. And on the other hand, iodination has another problem, and that problem is iodination. We discussed in one of the question today also. But iodine is very less reactive. So if you want to carry iodination, means you need to you need to attach iodine, then the reaction will not proceed in forward direction. Okay, so direct halogenation you can do for for chlorination and bromination. You can put directly by taking them in the presence of Lewis acid. But there are some other indirect ways also to connect the groups which you want to get connected to the benzene. And that indirect question is synthesis using diazonium. Okay, what is this diazonium group? Yeah, tell me. And how it can help you to get Cl, Br, F or I attached to benzene. So let me tell you, this is an indirect way. This is not a direct attachment. So indirect way means first you're taking benzene. This is AR means an aromatic group. Okay. You are doing the nitration. Okay. This is the way we generate NO2 plus. Okay. HNO3 you take H2S4, which removes water and gives NO2 plus. NO2 plus is an electrophile, just like we have seen for in some last reactions. Br plus and Cl plus, they will get attached. Okay. So you will have nitrobenzene. I'm telling it quickly because this whole thing we will discuss it in detail. Okay, lot of detail in aromatic chemistry also, aromatic amines also, which is the chapter, upcoming chapter in your syllabus. Okay, and then what you do the reduction of this nitro group. Okay, reduction, for that reductions it can be simply represented by H, or you can write 10 or HCl or Fe or HCl. 10 HCl, FeHCl are reducing agent, good reducing metal, and just now we have seen zinc HCl. 10 HCl is a very famous reducing agent which is used to reduce nitrobenzene to aniline. Okay, now this aniline you have, this is a primary aromatic amine. 1 degree means this nitrogen is connected to only one side, it is connected to carbon, which is the carbon of the benzene ring. Okay, it reacts with the NaNO2 plus HCl. Okay, NaNO2 plus HCl or HNO2 is one and the same thing. And this is nitrous acid, which is not there in the lab, so you need to create it by taking NaNO2 plus HCl. It is same as HNO2, nitrous acid. So it is react with nitrous acid, and aniline is generated with the generated aniline is reacted with nitrous acid, and that will convert the aniline to diazonium compound. And this diazonium has N2 plus group directly connected to benzene. This is benzene diazonium chloride. Okay, how the diazonium is created? Let me tell you very quickly, because we are going to do it in detail in aromatic amines chapter. This is nitrous acid, and how this is created: NaCl and HNO2, and this OH will also get removed in acidic medium, but because H plus will come and join to OH and water will be removed. Actually, in acidic medium, OH is removed as water. You will end up with NO plus Okay, in same way, NO2 plus was also created in this above step. Okay, NO plus will now have a lone pair of nitrogen, which is outside the benzene ring, which can react with it. Okay, so pH and water will get removed. So this is how you get diazolia. But what's so special about it? Why we are using it? Because it at first glance it may appear that this step is quite cumbersome and quite long. Then why we are using it? Okay, if it is so inconvenient, it is so long, then why we are using it? It appears to be very long and inconvenient, but it has an advantage. And what is the advantage? This diazonium is N2 plus. Okay, and this N2 will take away the electron through which it is connected to benzene and will become neutral and will become N2, and it will break away from the benzene. Okay, it is unstable in short. And what is the reason for its instability? It is the N2 itself. You people know that our atmosphere has 70% more nitrogen, okay, more than 70% nitrogen. So why it is in such a large amount? Because nitrogen is very, 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 very stable. It is unreactive. So if you have N2 plus connected to benzene, what is going to happen? This N2 plus will break away as N2. Okay. Anyway, this is going to break. And what you do actually while preparing, you can note down. You keep the temperature low, 0 to 5 degrees Celsius, so that it doesn't break. Okay. Anyway, it will break. But during the preparation, during the synthesis, you keep its temperature low. Okay. Once it is prepared, you put the nucleophile or the group of your desire, which you want to connect to benzene. So this N2 will come out, you can see, and the nucleophile will get attached to benzene. And that's the way in which you attach groups to benzene ring. Okay, this is a very important reaction, series of reactions. This is known as, this whole procedure is known as synthesis using diazonium salt. Okay, so there are actually for Cl and Br it is just added just one more method. Okay, but there are certain group which can't be attached directly to the benzene. So for them, this is the sole way of doing, attaching them to benzene. For Cl and Br, it is just an additional way. Okay, because you can connect Cl and Br directly also to the benzene ring. Okay, but for other groups, it is a very important method. Okay, so let me summarize it quickly, and that will clarify all your doubts. So first you take benzene, you do its nitration by taking nitric acid and nitric acid NO2 plus you create by taking H2SO4, HNO3 H2SO4 mixture you take, that will create NO2 plus, and NO2 plus will get attached to benzene, so that will give you nitrobenzene. The first step is nitration. The second step is going to be the reduction of nitro group by 10 NHCl, and that will give you pH NH2. NO2 will get converted to NH2. Okay, and so you will have primary aromatic amine, which is aniline. The common name is aniline. This is the second step. The third step is conversion of NO2 NH2 to diazonium by reacting it with NaNO2 plus HCl or nitrous acid. Okay, to keep the temperature low so that the diazonium salt is prepared. This diazonium salt, the fourth step and the final step, you put the nucleophile of your desire. This N2 will come out and that nucleophile will get attached to the benzene. And that's how you do the synthesis using diazonium compound. Okay, so let's do one quick question and that will help you to have the, because it is a long process. Okay, it is not a direct process. So just do this question, 2-3 questions, which can help you to understand everything in a more better way. Now, what is going to be the answer of this? Which of the following reacts with NaNO2 plus HCl at 0 to 5 degree to form a diazonium salt? So from which compound the diazonium salt is created? Yeah, tell me.
Option B.
Yeah, option B, aromatic primary amine. It is created from aniline PHNS2, which is 1 degree amine because nitrogen is connected to only one carbon. So it is primary amine, and it is aromatic because this benzene is aromatic. Phenyl group is aromatic. Yeah, correct. It is not from nitro. Secondary amine can't give because the secondary amine have connected, nitrogen is connected to 2 carbon. It can't form N2 plus. And the amide also can't form N2 plus. Correct. And this question, which was just asked few weeks back in NEET examination, very simple question, but you need to be very alert. That's it. You need to be very alert. That's it. Otherwise, it is a very, very easy question. Very, very easy question. But you need to be alert to avoid mistake. So this diazonium compound, primary aromatic aliphatic amine. Aliphatic amine means the amines which are connected to alkyl group like methyl, ethyl, propyl, butyl, not the benzene. Simple aliphatic group. It reacts with nitrous acid to give unstable diazonium salt. Yeah, that's true. They will also form unstable diazonium salt because diazonium salt everywhere they are not very stable because they have N2 plus, and then N2 plus has a tendency to come out as N2. That's it. So they are unstable. So this statement is correct. Simple, very simple statement. The question may look very big, but it is very easy question. But still, everybody can do it wrong. Okay, you need to be very careful. You need to keep your eyes open. Okay, now the second statement, primary aromatic amine. Now that's what we have seen just now. When reacted with nitrous acid or NaNO2 plus HCl, which ultimately gives nitric acid, gives diazonium salt, correct? Which are stable even above 300 Kelvin. How much temperature is 300 Kelvin? Hanifa and Samira, tell me in degrees Celsius. So everything was correct. Everything was correct. Okay. Just the last statement 2 was correct. Just its last portion, just one temperature was incorrect. And that will make this whole second statement incorrect. Okay. Even if a small portion is incorrect, the whole statement is incorrect. Okay. Because you need to tell the correctness of the whole statement as a whole. Okay, so what is going to be the answer? Very simple. Statement 1 is correct and second is incorrect. That's it. So simple, but you need to be very alert. Very alert. Okay, to know this. Okay, diazonium. But on the next time we will discuss. Actually, this is today we just prepared diazonium. Next time we will discuss how this diazonium is converted to chlorobenzene, bromobenzene, iodobenzene, chlorobenzene. Okay, that we need to discuss. But today we were able to just prepared diazonem because it was very, very important, and it is not of this chapter. It will be useful for you in phenols. It will be useful for you in aldehyde ketones. It will be useful for you in amines. In all the upcoming chapter, it will be common thing in aromatic chemistry. Okay, so let me end today's class. I hope all of you understood well. Okay, and let's discuss it in the next class and how to get different aromatic halides from that. Okay, so bye bye everyone. Good night. Take care. Okay.
Thank you, sir.
Okay.